Physics is often concerned with the study of motion. Up until now, we've been focusing on linear motion, or motion in a straight line. But now we're going to change our focus a bit and look at rotational motion, when something is spinning in a circle or revolving around another object. This video will teach you some of the basics about rotational motion, kind of like we learned some of the basics of linear motion with kinematics at the start of the school year. For starters, before we can define any quantities, we need to start by defining what we call the axis of rotation. This is a point where all portions of your object will rotate around. Sometimes we'll use AOR for short instead of axis of rotation. The axis of rotation sometimes is located at the center of your object, like the CD, this image of the CD that's shown here. But other times it's located in different points that aren't at the center of your object. Think of a door, for example. The axis of rotation for a door would be at the hinges, which is definitely not at the center of your object. The important aspect of the axis of rotation is that any point that's on the axis of rotation is not moving. Now that we've defined that, let's talk about some quantities. Just like we did with linear motion, we are going to focus on three main qualities that we can use to define angular motion. Those quantities are displacement, velocity, and acceleration. When we're doing rotation, we use different symbols than linear motion. So for angular displacement, instead of an x like we commonly use, we will use a theta. The equation for angular displacement is that theta is equal to s over r. That s is the distance traveled by your object, the linear distance traveled, and r is the distance from the axis of rotation. We'll use this mainly when we have an object that is near the edge it's rotating. So in other words, if we had something standing on the edge of this CD here, we could talk about the distance it traveled, that would be this arc length here, and how that relates to this angular displacement theta. The common units that we'll use will be radians, or RAD for short. But just as with linear motion, there are some other units that can sometimes be used. For example, you may see something in revolutions, or rotations would be another name for that. An important fact that you must know is that 1 revolution is equal to 2 pi radians. Sometimes we use things in degrees as well, and so an important fact to know is that 360 degrees is also equal to 2 pi radians. When we use equations, we will commonly use radians rather than revolutions or degrees. Moving on to angular velocity. We learned linear velocity is the rate at which something moves, or the rate of change of an object's position. It's the exact same thing here. Angular velocity is the rate of change of an object's angular position. The symbol we use for angular velocity is a lowercase omega. It kind of looks like a W, but it has, for lack of a better word, wings on either side of it. When we're doing average angular velocity, we can calculate that with the angular displacement divided by time. Just like we calculate average linear velocity by doing the linear displacement over time. When I think about the units, I know that theta is measured in radians, and I know time is commonly measured in seconds. So the average unit, or the common unit that we need for average angular velocity is radians per second. Another very common unit that you might see is RPM. RPM stands for revolutions per minute. You will need to be able to convert from revolutions per minute to radians per second before we can do problems, when we need to make sure that our units match. Just as with linear velocity, we can talk about average angular velocity and instantaneous angular velocity. And those two words, average and instantaneous, mean the same thing as they did with linear quantities. So the average is when we have over a time period, whereas the instantaneous is at one specific point in time. An important note is that this equation is for the average angular velocity. So if you have an angular acceleration, you may not use this equation. This can only be used when the angular acceleration is 0. Now we're about to learn about angular acceleration. An angular acceleration has a symbol called alpha. So this equation can only be used when that angular acceleration, or alpha, is 0. Alpha is another Greek letter, and this is once again a lowercase letter. Moving on to angular acceleration, we now already know its symbol. You could probably guess its equation if you think about the linear version of this equation. We defined linear acceleration to be the rate at which the velocity changes. In other words, it was the change in velocity over the change in time. Looking at angular quantities, we have the change in angular velocity divided by the change in time. And once again, this gives us the average angular acceleration. Thinking about units once again, our common unit for angular velocity is radians per second, and we divide that by seconds per time, and so we get radians per second squared as our common unit for angular acceleration. A few more facts here before we move on. First of all, we've learned that displacement, velocity, and acceleration are all vector quantities. And that's no different for when we're talking about angular quantities. These are all vectors. But you may have noticed that I did not put vector symbols on top of any of these symbols. For the purposes of honors physics, when we're talking about direction of these quantities, we are simply going to use the directions of clockwise or counterclockwise. Just like in math class, counterclockwise is considered to be the positive direction, and clockwise is considered to be the negative direction. Just like on the unit circle, if you think of how you measure angles, the positive angles go counterclockwise, and the negative angles go clockwise. So for all of these quantities, displacement, velocity, and acceleration, if the problem does not specify that they're looking for a magnitude, then you must include either clockwise or counterclockwise as your direction. One final fact here before we move on, and that's the fact that any 2 points on a rotating object have the same angular displacement, the same angular velocity, and the same angular acceleration. So going back to the example that we had at the beginning of the spinning CD, any point on that spinning CD would always have the same of these 3 quantities. Once we learned about these 3 quantities back at the beginning of the school year, we then learned 4 equations that were really important and were really useful for us for the remainder of the year. We called these the 4 kinematics equations. Well, guess what? We can take these 4 kinematics equations and use them for rotation simply by replacing the linear variables with angular ones. So V final equals V initial plus AT becomes omega final equals omega initial plus alpha t. Delta x equals 1/2 VF plus VIT becomes delta theta equals 1/2 omega initial plus omega final times time. Delta x equals v initial t plus 1/2 at squared becomes delta theta equals omega initial t plus 1/2 alpha t squared. And lastly, v final squared equals v initial squared plus 2a delta x becomes omega final squared equals omega initial squared plus 2 alpha delta theta. I'm choosing to leave off the vector symbols here since we have some new variables so that we're not getting too confused with having vector symbols and brand new variables. But it's important to remember that if your direction is clockwise, you need to plug in a negative number for your quantity. And if it's if it's counterclockwise, you can plug in a positive value. We will practice using all of these equations and concepts in class. When you come to class, make sure that you bring notes that you took while watching this video and any questions that you had that may have arisen.